Hello, I'm Mr. Hotelling. In a previous video, you got an introduction to nuclear reactions. In this video, we're going to go into more depth and give you a simple method for balancing nuclear reactions. In the previous video, we learned that there are a series of nuclear particles. Well, it turns out there are quite a few more than were introduced in the previous video. In addition to a neutron, there is a proton. A proton can exist as a nuclear decay particle. We learned that in the previous video that an electron is also called a beta particle, or a beta minus particle. We learned that the helium nucleus is also called an alpha particle. Taking a helium atom and stripping away its 2 electrons gives it just the helium nucleus remaining. There is also another particle called a beta positive particle, or a positron, as it's known. We learned about a gamma particle in a previous installment, and they spoke about it as being light. Now, a gamma is a kind of light, and light is oftentimes referred to or referenced as being a wave, but it is also referred to as being a particle. We say that light has a particle wave duality. That means sometimes it behaves as a particle and sometimes as a wave. And that particle has a name, and that name is a photon. So a particle of light we call a photon. And this depiction here, what I like about it is it illustrates that the particle has a wave-type nature to it, but also that it's discrete. It seems to exist as an entity or a particle unto itself. We might even visualize this as being like a particle, almost with a boundary around it. And what's illustrated also in these pictures is that the energy of light, of a photon, is related to its frequency, or we could think of it as its color. So what we see here depicted are 4 different colors representing 4 different frequencies of light. So the energy of that particle is related to the frequency. Now, a gamma particle, a gamma photon, has a particular type of energy, and so it has a particular type of frequency, and gamma light isn't light that we can see. It's very high energy. And so that's just a little bit more about setting straight what a gamma particle is. It is light, but it's a particle, and we think of it as being more of a particle, certainly particle wave duality. And then lastly, we have this other type of particle called a neutrino. And that is just simply another particle. It can come into play in nuclear reactions. So every different nuclide we could come across could be written as in its nuclear form. And we have seen that this number that's located in this area is the mass number. So a proton has a mass number of 1, a neutron 1, electron 0, alpha particle 4, gamma neutrinos have 0 mass. This number in the bottom left we could think of as being the nuclear charge, or the charge it displays or has when it's in the nucleus. So a proton has a +1, a neutron 0, an electron would have a -1. Now, we don't generally think of an electron existing in the nucleus, but in the previous video they spoke about a neutron decaying to a proton and an electron. And so in that instant when that neutron is decaying, it is in the nucleus. So that's how we could have an electron in the nucleus, just for that instant when it decays. A beta positive, having a +1 charge. A helium nucleus consisting of 2 protons, of course, would have a +2 charge. And neither a gamma nor a neutrino has a charge in the nucleus. So this is the nuclear family of particles and a little bit more about what they mean. So now let's take a look at some examples. So we have here is a table from Wikipedia that lists the isotopes of hydrogen. And we see that there are two stable isotopes, hydrogen 1 and hydrogen 2. And there's a series of other nuclides, combinations of nucleons that exist, but they're not stable, and they undergo radioactive decay. And as we've seen before, we have the isotopic masses of them. But we are also given the mode that they undergo decay. When the nucleus decays, what type does it undergo? So hydrogen 3 undergoes a beta minus decay. Hydrogen 4 undergoes a neutron decay. And the daughter isotope is, one could think of each nuclide as being a parent giving birth to new entities, and those new entities are referred to as the daughter. So what comes out of the nuclear decay is the daughter. So the way we can write the reaction is we could start out with the parent product. And so let's do hydrogen 3. So we have hydrogen here. It is hydrogen 3. And since it's hydrogen, it has 1 in the nucleus, plus 1 charge. Now, when we do a nuclear reaction, how we keep track of everything is based on two of the most fundamental principles of understanding everything in the universe, and those are the conservation of mass and the conservation of charge, in this case, in the nucleus. So we have the conservation of mass in this turquoise color, and we have conservation of charge we'll track in the bottom. Now we are told here that the hydrogen 3 undergoes a beta minus decay. So we will write the beta minus symbol here. So the mass of beta minus is 0, and it has a -1 charge. And we know it turns into some other species. Now, this table is telling us what it turns into. But we could use this to determine what the species would be. So we have some unknown species, which I'll indicate here. Now, this is a simple mathematical equation. 1 equals -1 plus what number? Or what number plus -1 equals 1? Well, when we think about that, that's the number 2. 2 plus a -1 is 1. And 3 equals 0 plus 3. So whatever this species it turns into, it will have a nuclear charge of 2 and a mass of 3. Well, when we look at the periodic table, the element with the number 2 is helium. So our daughter product is helium-3. And if you notice, that's what we were given up above. But it's a simple matter to keep track and do the accounting of the nuclear charge on the bottom and the mass on the top. So now let us consider hydrogen 4. You may want to pause the video and try this yourself. All right, so here we have hydrogen 4. And since it's hydrogen, it has 1 plus 1 in the nucleus. It undergoes a neutron decay, and a neutron has 0 charge in the nucleus, and it has a mass of 1. And in case we forget, we could go back to our list of family particles, and we see there's the neutron 1, 0. And that is going to turn into some other species. And so 1 equals 0 plus 1. 4 equals 1 plus 3. So this element that has 1 proton is hydrogen. So hydrogen 4 decays to hydrogen 3. And if we check the list up here, that is indeed what it says happens. So this is a sensible way to apply the rules of conservation of mass and conservation of charge to balance out a nuclear reaction and determine what the daughter products are.